Hey guys, welcome back to quantum mechanics. Um, so today we're going to start with a brief introduction into a very important topic, especially for condensed matter physicists, but also people that study scattering experiments where you're looking at uh, states that have identical particles in them. And so this section of the class is known as the identical particle section. and so that means that we're done with scattering. I didn't realize last time that that was our last lecture on scattering. But I put a homework problem set in the Dropbox, and it's fairly straightforward. If you have any problems, though, just feel free to contact me. So this lecture is for Monday, the 28th. I will be back a week from that day. So I'll be back and we'll start to have regular classes the next Monday. I'll send out an email just in case nobody watches these lectures, which better be. Okay. So like I said, it's going to be a brief kind of just quick introduction. I don't want to get too heavily into stuff today, but we will. Okay, later on. Right. So this is we're going to start to talk about identical particles or systems where we have a bunch of identical particles. This is from a movie from the 80s where Arnold Schwarzenegger and Danny DeVito were twins separated at birth. It's a classic. If you haven't seen it, go watch it. Okay, so like I said, so today we're going to start to talk about systems of identical particles. And what we're going to see during these discussions is that there are some very surprising effects in quantum systems where you have identical particles, compared to classical systems. A lot of the stuff that we're going to do, we're going to be building up to this formalism known as second quantization. And second quantization plays an extremely important role, not only in condensed matter systems where you have, a lot of identical particles, and so that would be a lot of times they use what's called density functional theory. But like I said, second quantization also has applications, and it's really the kind of foundation of quantum field theories. And then finally, in the process, so our goal, kind of the capstone project, if you will, is we're going to quantize the electromagnetic field. Okay, so we all know in classical mechanics that we can have identical particles. You can imagine having, a bunch of marbles that are exactly the same. But these particles don't lose their individuality. In other words, we can take these particles, we can number them, we can follow each of the particles along some trajectory, along some path, and we would know at all times which particles were which, right? But in quantum mechanics, the situation is completely different. And this is solely due to the uncertainty principle, right? Because as soon as we can, locate, or what's the word I'm looking for? Yeah, we can locate two particles, two identical particles at one time, right? But as soon as we do that measurement, as soon as I say that's particle one, that's particle two, I've destroyed any information that we had regarding their momentum. In other words, their trajectory, right? So if later on we go and we measure the position of these two particles, we're not going to know which one was which, right? And that's all due, like I said, to the uncertainty principle. So, so again, losing, once we locate a particle at a particular instant, that means we've lost all information on the particle's motion, right? So in other words, even if we localize a number or system of identical particles, there's just no way that we can tell at some later time which particle is which, right? And so to help drive that point home, I drew this cartoon. So this is so let's assume that we have at time t1, we have a particle over here and a particle over here, and then something happens, is represented by this blob, and later on we measure the particles and we find one of them's here and one of them's here, right? So you can imagine that this is like a scattering experiment, right? But if these particles are identical, we don't know which path they took, right, in a quantum system. So in other words, they might have come in here, this particle might have come in and then kind of rebounded and gone this way, right, and this particle came in and went that way, or maybe they crisscrossed, maybe they crossed paths, right? And in quantum mechanics, we can't distinguish between these two scenarios because we can't follow the particles at all times, right? Okay, so in quantum mechanics, what we're saying is that in principle, there's no possible way to separately follow each of these similar particles, right? And there's no way that we can distinguish them. So in contrast to classical particles, which I said basically keep their individuality, right? In quantum mechanics, identical particles kind of lose their individuality, right? So we can't really pick out and follow one particular particle. They all just kind of get lumped into this this kind of conglomerate of a state, right? So these particles are losing their individuality. If you're a Star Trek fan, I always like to say that identical particles are kind of the Borg of the quantum world. All right, so if you're a Star Trek fan, you get that. If you're not, don't worry about it. It might be on a quiz or a test. Okay, so there's this thing that we call the principle of, I'm gonna try to say this, indistinguishability of similar particles. So it's a principle that we can't distinguish similar particles in quantum mechanics, right? And it's a fundamental principle, and it plays a role in how we construct systems of many particles, systems of many identical particles, I should say, right? And to see this, we always start with the simplest case, which would be a system of two identical particles, right? And if we have a system of two identical particles, we can basically write the wave function of the system in one of two ways, right? We can write the state, and whichever way we write it, if we interchange the two particles, because they're indistinguishable, the state itself should remain the same, right? So those are the principle. This is the principle of particles that we can't tell apart. That's what I've just renamed this. Okay. So in wave mechanics, what does this mean? So it means that the wave function that we would write down, say for a case where particle one has some, so these C's here are kind of generalized coordinates, so they can be represent the three physical coordinates, but they can also incorporate spin, which we'll see is a important thing to incorporate when you're writing down, the states of many particle systems. But basically, what this principle is telling us is that the wave function that we would write down for the entire state, if we exchange the two particles, right, it has to be the same state, but since we're dealing with probabilities where we take this thing modulus squared, that means that these two states can differ, but the only difference can be a phase factor, which I'll write as the normal e to the I alpha, where alpha here is some real number. Okay, so what can we say about this phase? Well, we know that if we repeat the exchange, right, so if I go and exchange C2 and C1 again, I should get back to the original state, right? But I would pick up another factor of this phase factor, right? So I would get something like, oops, what was it? So I would go, here's my two transformations. So I flip C1 and C2. I pick up this factor of e to the I alpha, and then I do another exchange, and I get e to the 2I alpha, right? So what is that telling us? Well, it's telling us that e to the 2I alpha, whatever alpha is, that thing has to be equal to 1, right? Because I do two exchanges, and I get back to the original state. Right, so that means that if I take the square root here, I get e to the I alpha is either plus or minus 1, right? And so, what am I doing? Yep. So that means that these two states, they can differ by a phase, right? And that phase is either going to be plus or minus 1, right? So this is telling us that we have two possibilities, right? Either the system's wave function is going to remain unchanged. In other words, we're getting this plus sign, right? And in that case, we say that the state is symmetrical under this interchange, right? Or we have the other case where under the interchange, we pick up this minus sign. And in that case, we say that the system is anti-symmetrical under this interchange of particles or interchange of the labels of the particles. It's important to note that when you have a system of identical particles, they fall into one of these two categories. There's never so the way to say it is that wave functions for a complete large system of identical particles always has some definite symmetry. It's either completely symmetric or it's completely anti-symmetric. Right? There's just no examples of systems where systems of identical particles where you have some mix of the two, right? Where you'd have some linear combination, some part that would go transform as symmetrical, and the other part that would transform as anti-symmetrical. That's just never been observed, and so this kind of this statement here about the definite symmetry is just an empirical fact, right? It's just something that has been observed in nature, and we build it into our theory, and we'll discuss this more later on when we get to start to talk about fermions and bosons. Okay, so let's try to put this into some notation, right? Try to come up with a more quantitative of way of doing things. Okay, so we're going to consider a system of two identical particles, right? And I want to work in my ket notation. I don't want to work with wave functions just yet. Okay, so let's write down states in our ket notation. Okay, and we're going to suppose one of these particles, and I'm just going to call it particle 1 for now, is characterized by some collective index k prime. Okay, so k prime is like all the quantum numbers that we can specify in one index. Okay, and likewise, we can say that particle 2 is characterized by k double prime. Right. So if that were the situation, I would write down kind of a composite state for our total system that would look something like this, right? It's kind of two one particle states that I've glued together, right? And I've put the labels here 1 and 2 to distinguish that this ket is the ket in the space that particle 1 lives, right? And this ket is a ket in the space that particle 2 lives. Okay. Right. However, so I've been saying that, this is particle 1, this is particle 2. We've been talking about this for a few minutes now. We know that in a quantum system, there's no way that we can distinguish these two particles, right? So how would we build this into our theory, this statement that, we don't know if particle 1 has k prime or particle 1 has k double prime, right? So what we would first do is we would also want to include the exchange state, like I said, the case where particle 1 has k double prime and particle 2 has k prime, right? And now, so let's say, okay, so suppose we do a measurement of this of K of the system, whatever K is. It might be, some spin eigenvalue, or energy eigenvalue, or something like that, right? And when we do this measurement, we're going to measure it for all particles in the state. So let's say we might have, in one case we would obtain K prime for one particle and K double prime for the other, right? But we don't know, beforehand which state the system is in, right? We don't know if we picked out particle 1 that has K prime, or if we picked out particle 2 that has K prime, right? And the same thing for K double prime, right? And in fact, for all we know, that and in general, the system's going to be in a linear combination of these two states, right? So in general, we would want to write down something that looks like this if we wanted to be completely general. Okay. It turns out that, independent of how we write these, the state down, with if we use this, or if we use this, or if we use a linear combination, anytime that we do a measurement, we're always going to, get the same answer, right? So in this particular case, we would get one particle with K prime and one particle with K double prime, right? And this is something that's known as exchange degeneracy, right? So that, in other words, we have 3 different looking states, right? But they all result in the same eigenvalues when we do measurements. Okay, and we'll come back again. Like I said, we'll come back to a lot of this stuff. This is just kind of an overview, and we're going to put all this stuff to use when we start to build up a theory towards second quantization. Okay. All right. So let's start to do this. Start to build, kind of a true quantitative theory, or quantitative understanding of this exchange symmetry and how it works. Okay. And to do that, we're going to define an operator. It's called a permutation operator, right? And so we're going to work in a 2-particle state for now. So I'm going to label this as P sub 1, 2, right? And this operator is defined through its action on a 2-particle state. So in other words, say we have our state with K prime, particle 1 has K prime, particle 2 has K double prime, right? And I operate on this state with our P12, right? And P12 is defined to basically change the labels on these kets, right? So it's basically flipping these labels, right? So it's you can think of I've flipped the labels and then moved the K double prime to the front because it has a label of 1. The order of these guys doesn't matter. Okay. So basically what it's doing is just flipping the indices, or you can, let's just keep saying that it's flipping the indices. Okay. So in other words, particle 1, which initially had K prime, becomes particle 1 having K double prime, right? And vice versa is the way we would say that. Okay. And notice that, like I said, P12, this should be subscript, has the effect of just basically interchanging the labels, right? So it's taking the particle 1 and switching it with particle 2, right? The labels, not the actual particles, right? And just from common sense, we basically require this permutation to have 2 properties that we're kind of used to from. So this has a lot of similarities with parity, right? So if I flip 1 with 2, or if I flip 2 with 1, I should get the same thing, obviously, right? And if I do this interchange twice, we've already seen that I should get the identity operator back. Okay, so these are properties that we expect P12 to have. Okay, so all right, so let's consider our 2-particle state, right? And again, we're going to assume that these 2 particles, which we're going to write as 2 single particle states, and let's assume for concreteness that these states are eigenstates of some particular operator, and then let's just call that operator A, right? But each particle has their own version of this operator A, right? So in other words, I have an A1 that operates on kets that live in the space that particle 1 lives in, and I have an A2 that lives in the space that particle 2 lives in, right? So in other words, if I take A1 and I operate on my composite state, it's only going to operate on this guy, right? So you can think of this, I think when we talked about spin, we talked a little bit about this, where you can write it like this, right? But really what it is, it's a product of this guy in space 1 and an identity operator in space 2. Okay, so this guy is only really operating on this. And so since it's an eigenket, it pulls out a value, eigenvalue of A prime, and we're left with the state, the original state, right? And likewise, A2 would pull out a double prime, okay? All right, so what I want to do is, we know how the states act under this permutation operator. Now what I want to do is understand what happens with these operators, A1 and A2, when we operate on them with P12. Okay, and to see that, let's look at the case where, and this should be, so on this left side here, I just noticed that these A's should have subscripts of 1. Okay, so let's take our definition of A1 operating on this state and hit it from the left with our exchange operator, or right. So A1 operating on this thing gives me A prime and then the original state back, right? And we know what P12 does on this side, right? It's going to flip. So it can, this is a number, right? So it can pass through the number, and then it's going to hit the state and it's going to flip it, right? So now particle 1 has double prime, A double prime, and particle 2 has prime, right? On the right-hand side, we don't know what the commutation relation is between P12 and A. We don't know if they commute or not. So, but what we can do is use that property that says that, or we can just basically use definition of operator and its inverse being, identity operator. So we're going to insert 1 here in the form of P12 inverse and P12, right? And then P12, we know what it does on this. It flips the 2 states, right? And then finally on this last line here, I've gone backwards. So A prime multiplying this stuff is the same as the operator A2, acting on this state, right? So you can see what I'm doing. I'm going from here to here, right? And at that point, what I can do now is I've got identical states on the left and right-hand side, and I can write down an operator equation, an operator identity. And what we see is that this permutation operator, this P12, when we sandwich our operator A1, this should be A1, between P12 and P12 inverse, in other words, if we're doing like a similarity transformation, we get the operator 2, right? So this permutation operator is basically changing the labels on our operators in this 2 particle state. Okay, so a lot of times we're going to focus on the 2 particle state, but everything that I'm saying here is applicable to particles with 3, 4, 5, however many particles you want states. Okay, so that does it for today. It's just a short little kind of, to get the ball rolling. And next time what we're going to do is we'll start building these states and start to talk about the differences between spin 1/2 particles and spin 1 particles. Okay, so like I said, there's a homework in the Dropbox. I'll send out an email. I've decided to not give a midterm, so don't worry about a midterm, and I'll be back next Monday, and then all the fun will really start. Okay, all right, so hope everybody's doing all right. And if you have questions, let me know. If not, I'll see you in a week. But I'll see you next time on Wednesday for another one of these recorded lectures. All right. Bye.